Hello everyone. In this video, I shall be explaining you what are multivibrators, the various types of multivibrators available, and the working of transistorized astable multivibrator, followed by the expression for frequency of oscillations for a transistorized astable multivibrator. So at the end of this video, students must be able to explain the working of transistorized astable multivibrator. To get started, we need to know what are multivibrators first. Basically, a multivibrator is a system that produces an oscillatory signal offering us only two states called high and low as an output throughout its operation. It is very important to note that multivibrators are waveform generators which are non-sinusoidal. As shown in figure 1, which is a square wave, could be one of an example of a multivibrator's output. There are basically three types of multivibrators. The first is a stable multivibrator. This kind of multivibrator produces square waves or a rectangular wave that has some sort of duty cycle which is either less than 50% or more than 50% or even equals to 50%. This type of multivibrator doesn't require any external input for its operation or for the production of the output waveforms. So we can summarize the features of this astable multivibrator as follows. This is self-triggered, it doesn't require any input, and hence it doesn't have any stable state as an output. And it has some frequency for the output signal. And whenever we have frequency for an output signal, we definitely have duty cycle associated with it. The second variety of multivibrator is monostable multivibrator. This kind of multivibrator, unlike a stable multivibrator, is not self-triggered. It needs some manual intervention or an external trigger to provide an unstable state, which is a temporary state, and after a certain timeout period, it gets back to its own stable state. So the features can be summarized as it requires manually triggered, it needs only one input, it has one stable state. The frequency and duty cycle are conditional, that is, depending upon the trigger input, we can either consider the output frequency and duty cycle are present in the waveform or not. The third variety of multivibrators is bistable multivibrator. So as the name indicates, this kind of multivibrator has two stable states. Therefore, the features can be summarized as below. It is of course manually triggered like monostable multivibrator. It requires two inputs. One could be set and the other could be a reset input. Therefore, it has two stable states. The frequency and duty cycle are again dependent, similar to monostable multivibrator. Let's have a brief overview of the waveforms. Before that, think on how the waveforms of these kinds of multivibrators appear like. Here is the answer. The first waveform shows that the output waveform is constantly altering in between 0 and 1, and this happens because there is no manual intervention. As soon as the supply is applied to this kind of multivibrator, it starts producing such astable states throughout its operation. The second monostable multivibrator provides an unstable state when you provide a manual trigger at this point, and it remains in the unstable state until the time constant, which is defined by the RC network, that is a part of a monostable multivibrator circuit. The third kind of waveform is bistable multivibrator. Whenever you apply a trigger pulse at this point, it gets transited from 0 to 1 whenever the first trigger pulse is applied. When the second trigger pulse is applied here, it transits back again to a 0 and it remains there forever until a third pulse is applied at this particular third state to transit the output from 0 to 1 again, and so on. Now, let's have a brief overview of how a transistorized astable multivibrator is built. The circuit is basically built up of transistors Q1 and Q2, capacitors C1 and C2, and resistors R1, R2, R3, R4. Figure 3 shows such a circuit, and here before starting we need to make certain assumptions. That is, C1 must be equal to C2 and R2 must be equal to R3. We can split the working into three basic conditions, that is t less than 0, t equals to 0, and t greater than 0. The condition t less than 0 talks about a condition when Q1 is off, therefore the output across its collector O1 is high, and Q2 is on, that is, the output across its collector O2 is low. This basically describes the circuit when this circuit was being used in a previous case when the circuit supply is off. So if we assume that this circuit was previously under use at t less than 0, then the animated path is showing how capacitor C1 can charge and attain the polarities. So currently capacitor C1 has attained a charge where its left plate is held at positive VCC, considering that there is enough less amount of drop across R1, and its right plate is held at a potential slightly above the ground, that is zero point 0.7 VCC. Because of this VBE junction of Q2. Now when power supply is applied to this transistorized astable multivibrator, that is at t equals to 0, transistor Q1 is turned on as it is assumed to have more conductivity as compared to Q2, because of which the output across O1 becomes low and the output across O2 becomes high. This causes the current flowing through R4 to flow through capacitor C2 and then charge capacitor C2 with its right plate positive and left plate negative. In the meanwhile, the current also flows through R2 to drain the capacitor charge that this C1 is holding. As shown in the animation, it is very clear that capacitor C1 is now trying to charge from minus VCC to a positive of VBE junction. That is, if you consider capacitor C1 holding a charge of plus VCC with the given polarities, then after a certain moment of time when the power supply is applied across the circuit, Q1 gets turned on, which causes a change in the polarity of capacitor C1. So here, as per the polarities shown on capacitor C1, the positive energy that is available on C1 cannot exceed more than 0.7 volts. As long as capacitor C1 starts charging with the right plate positive, the moment when it comes to 0.7 volts, it is going to bias transistor Q2 directly as it is connected to the base of transistor Q2. This causes a switching action, and this is going to be the start of the next half cycle. In this condition, at t greater than 0, transistor Q2 is on, therefore its collector output O2 is low, and transistor Q1 is off, therefore its collector output O1 is high. And the similar conditions that were prevailing across the initial section of the transistor Q1 have appeared across this second section now. This causes capacitor C1 to charge again in the previously decided kind of a case. In the meanwhile, the current flowing through R3 is also going to charge capacitor C2 with reversed polarities as shown in the animation. Now, once capacitor C2 has charged by having its left plate positive and right plate negative, the maximum charge that it can attain is again positive VBE. This causes turning on of Q1 and turning off of Q2. This is how transistorized astable multivibrator runs, and the output can be obtained either from O1 or O2, and this condition appears throughout the circuit's execution. Now let's have a quick look at how the frequency of oscillations can be obtained. In this, it is very clear that initially capacitor C1 holds some charge by having its left plate approximately equals to VCC minus VBE. This happens when t is less than 0. When power supply is applied, that is at t equals to 0, Q1 is fully turned on. The right end of capacitor C1 approaches. VC is at minus VCC minus VBE. When t is greater than 0, Q2 is turned on, starting the second half of the cycle. So that now capacitor C1 charges from minus VCC minus VBE plus V saturation to VBE. Now it is very important to note that capacitor C1 tries to discharge or charge from minus VCC to positive VBE, and then it should start to charge towards positive VCC. But as capacitor right plate is connected to the base of the other transistor, capacitor cannot charge till positive VCC. So this results to a halfway charge of capacitor in both the cycles, resulting in 0.693 into the time constant. So this is the time constant, or simply T on period. The same is going to be the period for T off. So addition of these two on and off periods is going to give a total time period of 1.38 into R into C. Therefore, the frequency is the reciprocal of the total time period, and the frequency of oscillation expression comes to be F equals to 1 by 1.38 into R into C. Thank you. Here is the assignment. Considering the base resistors are 10 times greater than the collector resistors, identify what happens in between the time moment t equals to 0 until Q2 switches on. Thank you.